All right, today's problem is construct tree from pre-order and post-order. Those would be traversals. Difficulty medium. Accuracy, wow, it's very high. It's almost 80%. I have to admit it's going to be higher than my accuracy because I got a little cocky and just submitted this a couple of times without doing a compile check. So yeah, anyway, given two orders, two arrays, I'm sorry, pre and post, that represent the pre-order and post-order traversals of a full binary tree. Your task is to construct the binary tree and return its root. Note, full binary tree is a binary tree where every node has either 0 or 2 children. Pre-order and post-order traversals contain unique values, and every value present in the pre-order traversal is also found in the post-order traversal. Okay. In the absence of an in-order traversal, you can't, I mean, in general, you can't construct a unique binary tree from a pre-order and post-order traversal, although it's possible that, with a full binary tree, you can. I'm not sure. But in any case, we can construct a tree. So that's what we will do. Let's talk a little bit about traversals. There's three main traversals that you need to be aware of: pre-order, post-order, in-order. The pre, post, and in refer to in what order is the root visited. So in a pre-order traversal, you visit the root and then the left subtree and then the right subtree. So root, left, right. A post-order traversal, you visit the left subtree, then the right subtree, then the root, left, right, root. In-order traversal, left subtree, root, right subtree. All right, so we can take a look at one of these, and you can follow along here in the traversal. So a pre-order traversal is root, left, right. So root is 1 and then left. 2, we visit the root, left, we visit the 4. Okay, we're done. Back up, and then we visit right. So that is the 5. Now we are done with the root and the left subtree. So now we visit the right subtree. Root 3, left 6, right 7. All right, post order. Post order, you visit the root last. It's right, left, root. Okay, so we don't visit the 1. We go to left. We don't visit the 2. We go left. All right, now we visit the 4. Now, again, we still don't visit the 2. We visit the right, which is a 5. Now we visit the root, which is 2. We still don't visit the 1 root. We go to the right subtree. Now we don't visit that root either. We go left 6, right 7, back up to the root, which is 3, and back up to the root, which is 1. So you can see that in the pre-order and post-order. All right. Number of nodes will be between 1 and 10 to the third, 1,000. Pre and post. Okay, so yeah, the numbers in the nodes will be between 1 and 10 to the fourth, 10,000. Expected complexity, linear auxiliary space. Linear, we're going to use a map, and that would account for the auxiliary space. The topic tags don't really reveal anything there. All right, I want to get this so we can see the code, and I want to do this second one. We can see everything there except this. We can fix that. All right, that's fine. Yeah. All right, what do we have here? Here's what the nodes look like. There's an integer data element and then left and right pointers. Okay. Constructor Just pass in a value, it'll create the node, it'll set the left and right pointers to null. Here is our main method. We've got some class variables. All right, so input is the preorder and the postorder. You could, if you want to, pass the preorder and postorder to the build method over and over, but they're not going to change, so I set them to class variables. Put them up here. We have class variables. We have another class variable, which is this map, integer to integer. What is that going to do? Well, all right, we're going to call this method. We're going to set those class variables. We're going to create a hash map, and we're going to create a map. I mean, the preorder traversal is really going to drive the building of the tree, but we need to be able to find nodes quickly in the postorder traversal. And the way we do that is to create this map. We will iterate through the postorder traversal, and for each element in the postorder traversal, we use the element as the key and the index as the value. So based on having the node value, we can quickly find the index of that node in the postorder traversal, and then we call, we make the first call to build, and that is a recursive method. What are we passing in there? We're passing in indexes. We're passing in the index of the start index of the preorder traversal, the end index of the preorder traversal, the start index of the postorder traversal, and the end index of the postorder traversal. Now, to start with, let me get a pen here. To start with, pen. To start with, well, we're using the whole preorder traversal. That is from 0 to length minus 1. 0 to, and the length would be 7, so 0 to 6. Same thing with the post order. 0 to 6. So I guess I can put those here. 0, 6, 0, 6. All right. Now, our base cases are, if somehow the pre-start is greater than the pre-end, that's a problem. All right, we return null. I don't think that's going to happen. I mean, there's nothing in the description that indicates that we're going to get traversals that will actually not build a tree. On the other hand, there's nothing in the description that guarantees that we will be able to build a tree. If pre-start equals pre-end, then we have found a node that we want, and we will create, based on that integer at in the preorder, using the pre-start index, we'll create a new node. All right, root val. You know what? I should have scrolled this a little bit more. Yeah, let's do it like that. Let's erase these. Rewrite 0, 6, 0, 6. All right. Root val, pre-start. Okay. The first element in the preorder is the root of the current subtree. All right. Now, as we make recursive calls to this, pre-start will change. But right now it's 0. So pre at 0 is 1 right here. Okay, so the root val is 1. Again, that'll change. We'll have to build the right subtree, in which case we will pass in the 2, but this principle follows all the way through. 2. If we pass in 2 as the start index, then 2 will be the root of the left subtree. and actually, you know, eventually we'll pass in 4. 4 will be the root of the left subtree. All right, node root. So we create the root node containing a 1. Left root val. The left root val will be pre-start plus 1. And again, you can see that if we add 1 here, we're going to get 2. That is the root of the left subtree. If we started with the 2, the next node, the 4, is going to be the root of the next subtree. All right, so left root val is pre-start plus 1. Pre-start is 0, 1. So left root val is 2. Left root post index. All right, now we got to do a lookup. In the map of 2. So the 2 would be at index 2. Okay? Right here. Left size is left root post index, which is 2, minus post start, which is 0. So 2 minus 0 is 2, plus 1 is 3. Size of the left subtree is 3. That is correct. Post index minus post start, so that is 2 nodes plus 1. Okay. Now, we have enough information to recursively build the left subtree and the right subtree. So what are we going to pass in here? We are going to build pre-start plus 1 is 1. End will be pre-start plus left size. That is 3. Okay. And that is correct as far as building the left subtree. Starting with index 1, which is here, and ending with index 3, which is here. Those are the nodes that we need to build the left subtree. All right, post start. Post start is 0, and left root post index is 2. Okay. Now again, that is what we need to build the left subtree in the post traversal. That is post start 0, and post start 2 again is here. So that's what we need to build the left subtree. Okay. Recursively building the right subtree. The right subtree's preorder starts after the left subtree's elements. So what do we have here? You know what? In hindsight, I'm going to put the 0 and 2 here because they're messing up my ability to annotate the building of the right subtree. Right subtree. Pre-start. What is pre-start? Pre-start is 0 plus left size. Left size is 3. 0 plus 3 plus 1. So that is a 4. All right. 0, 1, 2, 3, 4. That is the start of the right subtree in the preorder traversal. Pre-end. Pre-end didn't change. It's still 6. So again, from 4 to 6, that will give us the nodes that we need to build the right subtree. Okay? Left, the right subtree's post order ends before the current root's post order. So what do we have here? Left root post index. It's 2 plus 1 is 3. Right? Post end minus 1 is 5. Right? So in the post order traversal, 0, 1, 2, 3 to 5 is the, those are the nodes in the right subtree. Okay? So we can recursively build that. It ends before the current root's post order. The current root, since this is the first call, is 1. All right, so we're not dealing with that in the post order. We have already created the root val here. It's 1. We are going to recursively build and attach the left subtree. We are going to recursively build and attach the right subtree. And that's it. So let's try and run this. Get rid of the annotations. And actually, we can get rid of the toolbar as well. And go ahead and submit this. This, I would say this is, they rate it as medium. To me, it's on the harder side of medium. You actually have to have some understanding of tree traversals to get this to work. But there you go. And as you said, well, attempts 2 out of 4. I did get a little overconfident on a couple of my submissions. I thought I had it, and I didn't bother to do a compile check. So I got a couple of compile errors on my submissions. Lesson learned. I've only done, well, anyway. What else can we say about this? That's about it. These are fairly common questions. They'll give you, LeetCode has these as well. They'll give you like a pre-order and an in-order, and you build the tree. They'll give you an in-order and a post-order, and you build the tree. I hadn't seen this one before, pre-order and post-order. But yeah, go ahead and like the video. Subscribe to the channel. It's free. And that's it. We'll see you next time.